Okay, so once you have your FBD, let's write down our equation here. Net force is Fn minus Fg. Question A says, find the acceleration of the elevator. Okay, well, what do we know here? It says the scale reading increases to 935. You observed this yesterday because the elevator is moving up. The floor is pressing up on you. Okay, so acceleration is the question here. So F net is ma equals Fn minus mg. So we're looking for A. So the acceleration is the Fn in this situation went up to 935. Okay, because that's the apparent weight. Minus 836, which is the true weight. That's just mg. Divide that by the mass of the person. Now, the mass of the person is not directly given, but you know that Fg is mg, right? So we can find the mass that way, Fg divided by g. What is the true weight of the person? 836, right? So then you'll go 836 divided by 9.8. That will give you the person's mass. And it is 85.31 kilograms. So I'm going to put that right here, 85.31 kilogram. Okay, so that will give us the acceleration of that elevator, which is 1.16 meters per second squared. Let's see what B is. As the elevator approaches the 74th floor, the scale reading drops as low as 782. Okay. Do you guys remember the fourth number that you had yesterday, the fourth reading? So the first reading was at rest, when the elevator was at rest. I said read that one, record it. And then the second reading was when the elevator just began to move, right? Whether it went up or went down. And then the third reading that you had was when the elevator was mid-floor, when it was constant velocity, acceleration is 0. You notice that it was the same as your true weight, right? And then the fourth reading was just before we approached that floor. So this is that one. So what happened was your reading, your apparent weight in number 3, okay, went higher because the elevator was pressing up on you. So going upwards, you weigh more right away. And then when the elevator is approaching the 74th floor, just before it stops, it's still going up, right? It slows down, it went down. What happened to the elevator? Decelerated, right? Because it has to stop. It had to stop to the 74th floor. Okay, so that's what we're looking for B. So find the acceleration of the elevator. Now, the free body diagram, we don't have to repeat here because it's the same thing, right? It's still going up. Your equation remains the same. So net force equals Fn minus Fg, still looking for acceleration. Same formula. Fn minus mg over mass. Okay, except the Fn now is what in our question? 782. So the reading went as low as 782. So we go 782 minus what is our true weight again? 836, right? Divided by the same mass, 85.31. You notice your acceleration is going to be a negative value. And this is exactly what we observed yesterday in the elevator, right? Okay, so negative 0.63 meters per second squared. Okay, that tells you the elevator was slowing down and then was preparing to stop, which makes sense. So it speeds up, constant, slows down, stop. That's what elevators do. Okay. What, do you guys remember the elevator's acceleration, our acceleration as it was going up? It's less than 1, right? It's only 3 floors, so the elevator is slow. We have a very slow elevator, which is not a bad thing. Okay, there you go. Number 2, Carl?
Number 2,
B, okay. D, the elevator descends, okay, we're looking at number 2D. So the elevator now is going down, accelerating at -2. Okay, that looks funny. It's a meter per second squared. What does the scale read? Okay, I'm going to do that here. Okay, so this is number 2D. Okay, so what's happening? The elevator is going down, so a quick FBD here. So you got your FG, you got your net force because it's going down now. You got your Fn apparent weight. Quick formula here is net force is equal to Fg minus Fn. We are looking for, it says, what does the scale read? We're looking for the Fn. That's the apparent weight. So isolating your normal force, you have Fg minus net force. Okay? So Fg, mg minus A, and what's our mg? This is the elevator, right? Oh no, it's the person. Sorry, it's a person. Number 2 is a person weighing 490. So the true weight is 490 minus, what is the mass of the person? 490 divided by 9.8 is the mass, which is just 50 kilograms. So this is 50 kilograms times, what's the acceleration of this elevator? 2.7, right? 2.7 meters per second squared. Okay, so it says here this is accelerating, the elevator descends, accelerating at, is this when the elevator, I'm just looking at the wording, the elevator descends, are we looking at this elevator's acceleration as the immediate acceleration, or do you think this is when it's approaching the floor? So that's what your question is, you're not sure, right? Now I look at it, it's accelerating at -2.7. So if I were to put that negative, if I put the negative sign right in front of that, we are then defining this as the before stopping to that desired floor, right? So if I put that, if I interpreted it that way, then that would be the deceleration just before it stops. Okay, because the elevator has to accelerate first. It accelerates constant and then decelerate and then stop. So I'm gonna keep that -2.7 there, and then what's gonna happen to the normal force then? So 490 minus brackets 50 times what did you get? Okay, so what did you get here? So when you get, so 490 minus, I'm gonna go brackets, 50 times 2.7 negative is 625. Okay, what is this person doing? The person is going down. What was the weight before? 490. So 490 newtons at rest, or acceleration is 0, constant velocity. Okay, so the person's true weight is 490, but when the elevator was decelerating as it was going down, the person's apparent weight became 625. Okay, I need you to make sure that if you were to leave this as -2.7, you got to define this as the before stopping. Look at your data from, you guys still have your numbers? Yes. I'm just gonna take a look at an example here. I'm gonna grab somebody's paper that I can read here that has, okay, I just grab one example here. So here's the data. Okay, so here's an example. Just grabbing someone's random paper. At rest, this is, what is this, going up. Okay, so this is going up, net force going up that way. So at rest, this is the number, and then the initial movement, it went up because the elevator is ascending, okay? And then the initial stop, it went down And then you weren't, I guess you didn't have to write down the fourth number, but if you were to write down the fourth number, did anyone write down the fourth number? Okay, here we go. Here's the number. So it was first 140. This is going up. Oh, that's gonna be, yeah, going up right here. So 140, it went down to 160, got heavier, right? Then constant, 140 again. And look at this one here. Went down to 120 when it was decelerating. This is going up, going up. This question that we have is descending. It's going down, so it's the opposite. It went heavier before it stops. What's the answer that I put on the back of 2D? 2D is 355. Okay, so I'm gonna do that other thing now. If you were to, this is 2D, I put 4. So for 2D, what's our equation again? Net force, so Fn is Fg minus. Okay, Fn equals Fg minus net force. Okay, so it's the same question, but this time it's interpreted differently. So Fn is equal to mg minus ma. Look what I'm going to do this time. What was the mass of this person? 50, right? So I'm going to put 50 kilograms. Okay, 9.8. I could have just put 490, I guess. Minus 50 is the mass. This time I'm going to put 2.7 going down. So this would be the initial movement. Meaning when the elevator was going down. Okay, so it was stopped and then the elevator started going down, and then your number is going to be 2.7, and the reason why it was negative was because of the direction. I guess that was confusing, and this will give you 355 Newton. Okay, but this is the definition of, so two different interpretation. So if I were to give you guys a question like this, I would make sure I define it properly. So on the worksheet, it wasn't that clear. Okay, glad you asked that one. Okay. Any other ones from this worksheet? Okay, we're okay from all of these? You guys got all the answers? All right. Okay, so a 55 kilogram person, got the mass, riding in a hot air balloon, and a scale shows this person's weight to be 549. Okay, so there's the Fg. The acceleration due to gravity is this, it's lower. Determine the magnitude and direction of the vertical component of the balloon's acceleration. So it's going straight up. Looking for the balloon's acceleration. Okay, so here's the balloon. What is the balloon doing? Going up. Okay, so we're gonna put net force. There's also a force going down, right? Fg, because we're still on Earth. What else is happening? So this is actually the person in the balloon, right? So even though the balloon is going up, we have the system is actually the person in the balloon. So we're looking at the person riding, and the person is standing on the floor of that balloon, right? So then the person actually has Fn, because the person is the system here, person in the balloon. All right, so what do we have here? Net force is equal to Fn minus Fg. We're looking for the acceleration of that balloon. So where do we get the A from? So we expand this, so this becomes ma equals the Fn minus mg. So it's the same equation as the previous one. Fn minus mg over m. Notice that a good strategy when you're solving for any physics problem is you write down all the equation to the point of what you want. Acceleration. Manipulate everything. Don't plug any numbers in until you get to the final manipulated equation that you want. So now that you're ready for acceleration, okay, what is the apparent weight of the person? Well, you see here the acceleration of gravity at the location is 9.79. So this is g when the balloon is high up. Remember, as you go up, your altitude will change your G, right? The G is different, so it's 9.79, not 9.81. So what would happen to the person's apparent weight in this case? Will the person be lighter or heavier at that G? When the G is less, when the person's up in that rising balloon, will the person weigh less or more? Less, right? Because less G. So if I were to calculate the mg at this point, I'm just going to use the person's mass. The person's mass is 55, right? So 55 times 9.8, this is going to be the Fg. I'm just going to show you the difference between the Fg and the Fn, okay? So this is the 9.8 if the person were standing on the surface of the ground. So this is 55 times 9.8, and it's 539 Newton. That's the Fg. What do we do for the Fn? We take the same mass of the person is 55. This time we use G. Okay, so the G is 9.79. It's going to be a small difference, but it's different. So 55 times 9.79. The person's apparent weight is 538.45. Okay, so that's what we put for the Fn. So 538.45 minus the true weight of 539 divided by, what is the person's mass? 55. So the acceleration is 539. What did you guys get? 538.45. I got negative 0.01 meters per second squared. This person is going up. Let me read the question again. Oh, wait a second. I missed that one. Yeah, the Fn is actually given here. Okay, so then the true weight will be different. So then we're gonna use, okay, that changes the question. Okay, let's erase that because we actually have the information here for the Fn. So the Fn is 549. So I didn't need to calculate that because we actually know it. Okay. So Fn is, oh, it's right here. The scale. So 549 minus, what do we put for the weight of this person? The weight of the person then will be the 55 times the, right here, 55 times 9.79, which is this one right here. This is the true weight of the person at that altitude, so which is 538.45. Okay, that's right. The person here, we're going to take this out because the person is not standing on the ground. So we're going to look at the true weight of the person here because the apparent weight is already given. There you go. 549 minus 538.45 divided by 55. There we go. Okay, missed that one there. So sometimes what I do is sometimes when before I should have read the question twice, especially when it's pretty complicated like that. It's establishing what is happening. That's the main thing. So we're good to go.